Hello. In this recording, I am going to talk about how a carboxylic acid reacts with a base to produce a carboxylate salt and water. And I see that I have some image problems here for a second, so I am just going to there. I'm not really sure what was happening, but you couldn't see all of this, so there we are. So there's a practice question that said, in this acid-base neutralization reaction, this carboxylic acid, which has three carbons, so this is propanoic acid, is going to react with sodium hydroxide, which is a strong base. So let me engage the pen. I don't know what I'm doing. I think I zoomed something. Oh my goodness. Sorry about that. I think I unzoomed now. Pen. There it is. Sorry about that. I'm going to write with purple today, I think. Let me see how it looks. That looks okay. Alright. So, in this reaction, here we see acetic acid, which is, again, the common name for ethanoic acid. It's the primary ingredient in vinegar. Most household vinegars are a 5% solution of acetic acid. So 2 carbons. This is the hydroxyl group, the carbonyl group. This is what makes it the carboxylic acid. And it's going to react with sodium hydroxide. Now sodium is an ion and hydroxide is an ion. And in this reaction, what happens is the hydrogen ion, the proton, is donated to the OH part of the water, or of the sodium hydroxide, and we produce water. That leaves behind the sodium ion. And when this gets taken off, we're left behind with the carboxylate ion. So this is referred to as a carboxylate salt. And a salt is the reaction of an acid. It's the product of an acid-base reaction. When you react an acid with a base, you produce a salt and water. And what is unique about this carboxylate salt is that it will tend to be soluble in water even if the original carboxylic acid was not. Now that isn't the case in this specific example because acetic acid is a lower molecular mass carboxylic acid which is soluble in water, but there are sometimes some very long hydrocarbon chains that make up carboxylic acids that are not soluble in water, and one way that you can get them to dissolve in water is to react them with a base to produce a carboxylate salt. So let's look at this question. I am going to erase the pen. Oh, it didn't erase. Here, I'll just draw it out. So we have this acid-base neutralization reaction. We have, I am very sorry. Oh, now I'm discarding the ink notations. This is all over the place, and I'm not going to have time to edit it. So you will have to please be patient with me as I fumble through this video, and I thank you for your patience. So we have a propanoic acid, 3 carbons. In this condensed formula, one way you can represent a carboxylic acid is by this group COOH. So if I draw this out, I have CH3, CH2, C, there's one of the O's, OH. Alright, here's my carboxylic acid. And I'm going to react it with sodium hydroxide, which is the base. Again, in this particular acid-base reaction, this is acting as the acid. It is the proton donor. Oh, this is acting up and I don't know why. I don't know what I'm doing. I don't know what I'm doing wrong. Maybe I'm not holding the pen right. Oh, I'm sorry. So this is the proton donor, and it's going to be donated to this part of the sodium hydroxide. So we will get the carboxylate ion, CH3, CH2, C, O, O, and this carries a negative charge. With the sodium ion, this is our carboxylate salt plus water. So this carboxylate ion is negative charged, and it is bonding with the positively charged sodium. So one way that this could be written out in a long form, a carboxylate ion condensed formula would look like this: CH3, CH2, COO, and what you see is just a little negative sign here. So when we look at our original question, the one that fits that would be this one right here. Nope, that's not true either. It's a trick. This is not the correct way to represent a carboxylate ion, and neither is this. This is the correct way, and so is this. However, this has 1, 2, 3 carbons, and this only has 2 carbons, so that can't possibly be the product, which leaves us with this. And I'm not crossing it off, I'm circling it. Please just imagine that this line is creeping up a little bit there like that. So one thing that is significant about this is that the salts will be water soluble. So here's an example of octanoic acid, a longer hydrocarbon chain, which will be insoluble in water. So if we react it with a base, we can produce this carboxylate salt, which is soluble in water. And you may have seen the demonstration in the lab already, in which some salicylic acid was taken. So salicylic acid happens to be a benzene ring with the carboxylic acid like this, and it's a hydroxy group here. So this is another name for this is 2-hydroxy benzoic acid. So I took some salicylic acid, or if you didn't see this yet, you will see this demonstration, and put it into water, and it does not dissolve at all. It's just a white, clumpy, gunky mess. And when I added the sodium hydroxide to it, it all dissolved. So we produced a carboxylate salt in which we had, I feel like I'm drawing like a kindergartner here. So we had the carboxylate ion. This hydroxy stays the same, and the sodium, and this made it water soluble. Then in that demonstration, some hydrochloric acid was added back to it, and hydrochloric acid was a source of hydrogen ions, which then got put back on to this to produce this again. So once we got rid of the base and we started adding hydrogen ions back onto this to produce that, it formed a white gunky precipitate. So it came out of solution. It was no longer dissolved, and we saw that being undissolved again. So this is a way that we can take larger carboxylic acids and dissolve them in water if we need to by adding a base. So aspirin works like this. One of the active ingredients in aspirin is salicylic acid, and it has a limited solubility in the stomach because it's an acidic environment. When it gets into the small intestines, it's more of a basic environment, and it then can dissolve, and then the carboxylate ion will make its way to the body, where it can be used to reduce fever and be a pain reliever, and also reduce inflammation. So again, the goal of this was to show how a carboxylic acid can react with a base to produce a water-soluble salt and water. Thanks for watching.